This is our capacitor AC circuit. Hopefully you've looked at the resistor circuit first, otherwise some of this might not make too much sense. Now, to look at this circuit, we have to go back to thinking about charging of capacitors. And remember the one curve I said you guys needed to remember was this one. Time against voltage for a capacitor, and that it takes time to charge up. And therefore it takes time for the voltage to build up. Now, with the current, we had that graph that dropped down like that. These are both exponential graphs. So which one is maximum first? And I think you can see that it's your current. At a given time, this time comes before this time. So if this is the same time, which it is, then this one's at 0 when this one's at maximum. A little while later, this one has dropped down, but this one has gone up. So if we're going to draw a little phasor diagram for the charging of a capacitor, and with alternating voltage you're going to have charging, discharging, charging, discharging all the time. But if we're going to draw a phasor diagram, and if the little red one is my current, then the current will reach maximum before the... So as this rotates up here, if the rotation is this way, alright, then the current's going to reach maximum half a cycle later. I don't know why I always have my current here, but half a cycle, quarter of a cycle later, sorry, it's going to reach maximum. And at that point, your voltage is going to be 0. So your voltage across the capacitor, you put down here, we'll call it V with a little c. So voltage across the capacitor is 90 degrees behind the current in the capacitor. So they're not in phase. When the current is maximum, the voltage in the capacitor is 0. They're totally out of phase, and that's what these diagrams showed us when we did the DC capacitors. So let's draw ourselves a little graph of that. Now these graphs I draw come from our phasor diagrams. Once you've got this little phasor diagram, you can draw the graph. What you do is you just take a time that you're going to start with. Like we could say, if this is t equals 0, then our current at t equals 0 is 0, and our VC is negative. I'll do it on this bit of paper actually, that will make more sense. So if we're trying to do 3 parts of the cycle. So if we start at that time 0, then the current is 0, right? 90 degrees later, the current is going to be maximum, right? So that would be where the current would be. 90 degrees later, it's back to that. 90 degrees later, you can see the current will be maximum negative. So we can say that the current goes like that. If at this stage, the voltage is maximum negative, then we would have to start it here. And halfway, or a little bit later, it's there. Try and keep your amplitudes correct. So it's like that, right? So basically, we have it going like that. So this is our little phasor diagram, and we can make those graphs from this. All right. Now, that was voltage across the capacitor. This was current. Now remember, with the way we label the x-axis on these guys, you can label them as degrees. Theta equals omega t. Right? So this whole axis can be theta, which is equal to omega t. Now, if we just want to label it in terms of how many radians it is, we could also do that. Remember, the omega is how fast this thing's going around. Okay. Now, if you want to figure out things like omega, and we've got 140 cycles per second, we've got 50 hertz is a frequency in New Zealand for AC electricity. In America it's 60. They like to be different with everything, don't they? But what do those formulas mean? And to figure out how many radians, right, and periods and things like that, we need to go back to some of our formulas, right? Now, frequency is how many times a second. So that is F is equal to 50 hertz. That's a frequency. That's degree, so that would be 360 degrees. All right, that it does every second. So how many radians is that? All right, well, that's 2 pi radians. All right, so 2 pi f, so omega equals 2 pi f. All right, that's radians per second. Divided by 2 pi will give you the frequency, right? Do we see that? So frequency, omega, is radians per second. Divide that by 2 pi, and you've got the frequency. And frequency, as we know, is equal to 1 over t. So there's another formula, and this is one you should remember. All right, there's another formula which is t equals 2 pi over omega. What we're saying is the period is equal to 2 pi 6.28 divided by radians per second. That will tell you how long it takes for the period. But omega was equal to 2 pi f. So we can say 2 pi divided by 2 pi f. These guys cancel. And we get back to our old formula which said that the period was equal to 1 over f. Right? So with 50 hertz, we can easily work out the omega, can't we? So if you've got 50 hertz, that's 50 times a second. That's how many radians a second? That's 50 times 2.8. So omega equals 2 pi, which is 6.28, times the frequency, which was 50. 50 times 6, 300 and something radians per second. Right? Okay, next we'll do another little video on the capacitor and the inductor, then we'll put them together.